Hello. Today I will continue to give you the lecture in real analysis. At this point, I will pick up one point that related to real analysis, complex analysis, and topologies. Yeah, and that one is talking about limit point. Yeah. However, before I start to give you the definition of limit point and an example of it, I will give you a definition that is related to related neighborhood of a point. Okay, let's start together. Okay, let me write the title of something that we'll talk about. Limit point of a set. Okay, and as I told you before, something that I am going to talk here, I just minimize it in real number. Yeah. So every interval are open set. I mean every interval of real number are open set. I assume like this. Okay, let's start. First, I will give you the definitions of related neighborhood of point. Let x0 be any real number. A related neighborhood, okay, neighborhood of x0 is a set. Yeah, is a set contain all points near or around or near x0 except except x0 itself. Okay, that is if we talk in real number, we just talking about interval, right? I can say n epsilon x0, let me call it this, mean the related neighborhood of x0 equal to what? Equal to the interval x0 minus epsilon x0 plus epsilon minus a singleton set x0. Yeah. For any positive real number, we can say positive real number epsilon, and here epsilon can be the smallest one or the biggest one. Yeah, we just say that it's just a positive number. Yeah, to modify this, I can say like this. Yeah, I can write one line or one segment of real number, and I talk like this. In this one we call this point x0, and this one x0 minus epsilon, and this one x0 plus epsilon. Yeah, in fact this one, it is a neighborhood of x0. And now I just omit or I delete x0 from this. I got a deleted neighborhood of x0. You got it? Yeah, we have known about neighborhood of x0. Yeah, neighborhood of x0 on real number. It is in the form like this. It is the interval x0 minus epsilon, x0 plus epsilon. This is the neighborhood of x0. And now you just omit or delete x0 from this, you will get a deleted neighborhood of x0. Yeah, like this. Okay. So something that I have written here, just an example. I mean, a deleted neighborhood of x0 on real number. Okay. And as I told you, we just talking about real analysis, something that maximize to just on real number. So this is, we will use it later that it is what? The deleted neighborhood of x0 on real number. Okay? And in sum up, you just think like this. When you want to find a deleted neighborhood of x0, you just find a neighborhood of x0. Yeah. As I draw it here, and then you just delete it, or you just delete x0 from that neighborhood, you will get a deleted neighborhood of x0. You got it? Okay. And now we come into something that we want here, the midpoint of a set. Yeah, the midpoint of set. Okay. So I can say x0 is what? Is a limit point of the set S, capital S, and S here is a subset of what? Subset of all. Yeah, a subset of real number. Yeah, x0 is the limit point of a set S, where S is a subset of real number. If every, yeah, you can say it here, every deleted neighborhood, yeah, deleted neighborhood of x0 contains a point, yeah, a point of S. This is the definition of the limit point. It means that if you want to show that x0 is the limit point of a set S, you have to show that a general relative neighborhood of x0 contains at least one point of F. It means that at least one point. Okay, a point of X here, it means at least one point. Okay, okay. To know this clearly, just give you one example. Yeah. Okay, example. Find all the limit point of S equal to the interval, the open interval negative infinity to 1. Okay, S here is a subset of real number. As you know, real number is the open interval from negative infinity to plus infinity. And this one just a subset of real number. Okay, and now we want to find the all the limit points of S. it means that if S has at least a limit point, we can prepare it or we can take it into a set that we call the set of all limit point of S. Okay? Yeah, let me open this one. Something. I lost my eraser. I use this. Okay. Okay. I left this to you when I find the limit point of x. It just verify it with the direction of the limit point. Okay, I done only this one. Okay, so solution. What is the solution of this? Okay, the solution of this example. First one, I can observe this set. This set, in fact, as I told you, is the open interval from negative infinity to 1. So you can see, if you want to say that x0 is a limit point of a set S, if you can show that every relative neighborhood of x0 contains a point of S. Okay. So first, you have to choose a general relative neighborhood of x0. Yeah, that I have written in the previous minute that I opened already, right? Yeah. I call you for any epsilon positive and x0 is a real number or belong to real number. The general relative neighborhood of x0, yeah. So like this, or we can say like this one. Relative, yeah. Relative neighborhood of x0 is 1. Yeah, call it n epsilon x0 equal to 1. Equal to the open interval x0 minus epsilon, x0 plus epsilon, subtract with the singleton set x0. It means that a relative neighborhood of x0 is all point in this interval except x0, which is relative x0, right? Yeah. And now I will try to find first, I will try to find some limit point of S. I will show you that it is a limit point, and then I will check in general that all the limit points contained in any set. Okay? Okay. I say that 1 is what? From this, 1 is a limit point, right? Limit point of S. Yeah. Why? Why? Because you can check this by using this definition and you will know this. Okay. Sin. Yeah. You just replace x0 by 1. Here you get n epsilon. This one you can say epsilon. Replace x0 by 1, right? This one you get and epsilon equal to 1 minus epsilon 1 plus epsilon. Yeah, and you just subtract the set of 1, and this this n epsilon contain many points of x, because it's also a subset of real number. Yeah, I will check it's by drawing this one on the real line, but now I just conclude it first that it is true. Okay, so then from this, okay, and epsilon is what, we can say contain many points of s. Okay, let me check you by drawing some line, some interval of real number. Okay, let's see. Suppose this one, this is a real line, right? Real line number. Okay, and I check this one negative infinity. This one, let me check this one 1, right? And you take, yeah, 1 minus epsilon, 1 plus epsilon. Because epsilon is positive, so when you take 1 minus epsilon, maybe it here. Yeah. And 1 plus epsilon, maybe here. And where is s? Yeah. Let me see. Where is s? Yeah. This is s. Equal to t interval negative 70 to 1. Let's say negative 70 to 1, right? And now, and where is n epsilon? Here? Yeah. This one, and you just omit this one, you get this one and epsilon. And from this, you see, from negative infinity to 1, it is s. And from 1 minus epsilon to 1 plus epsilon, except 1 is an epsilon. And from this, you see, s and an epsilon have many common points. I mean at the same point. Yeah, this, we can say the intersection of these two sets, s and epsilon. This is the intersection of s and epsilon. And this set, they are intersect, and the intersect is not empty. So an epsilon contains many points of s here, right? This is the point of s2, and this is the point of an epsilon 2. So an epsilon contains the point of s in this line. That's why I say that an epsilon contains many points of s. Yeah, and from this, at the first, then I concluded that 1 is a limit point of s. And you just do like this. Do the same manner. Yeah, you can say, yeah, do the same manner. Yeah, for x less than or equal to 1, I can say x0. For x0 less than or equal to 1, x0 is what? Is a limit point of s. It means that for all real number that is less than or equal to 1, start from 1 and decreasing to negative infinity, they are all a limit point of s. Okay? So the limit point, I can say all limit point, yeah, of s say, yeah, the open interval negative infinity to 1 is containing, yeah, in the, yeah, you can say interval, yeah, negative infinity to 1 close. Yeah, we can say O half open close. Half open close, negative infinity 1. I mean open at infinity and close at 1. Yeah, half open close. Yeah. So all the points in this interval are the limit point of S. That is equal to the open interval negative infinity to 1. Yeah, you can check. Check by example. If you want to check less than or equal to 1, check 0. Yeah, 0, negative 1. Yeah, do the same manner as I did above, you will get it. So this is the set that contains all the limit point of S. Okay, thank you. See you for the next video.